for the path. You will notice that I already set h cross to 1. Okay, this was our point of view, and we had this expression. Then I described what kind of paths are included in this, and these are the paths which go forward in this time, going from x1 t1 to x2 t2. Then using that, we argued that there are two further conditions which emerges. The one condition is that the amplitude for the particle at the event x2 to be at the event x2 can be expressed as some integral over dt, just the spatial integral over x1 to pi over d of the amplitude for propagation, which is x2 x1 times psi at x1. And I pointed out that this tells you that given the state at x1, you can find the state here, which in turn implies that the equations which you are dealing with is first order in time. And the reason I am listing all this is none of this will hold in relationship case, which is what we want to do. This also implies a transitivity condition, which was x2 x1 is equal to integral over an intermediate spatial coordinates, which we denoted as y x2 y x1. And I emphasize the fact that the integral here is only over the spatial coordinates y, but the result has to be independent of y. And that put a very strong constraint on the nature of the amplitude. So we wrote that constraint in the following form. We said that if I take x2 x1 and I just do the spatial Fourier transform of that and write, let us say, dt of p over 2 by d, some function which depends only on the modulus of p, because for a free particle this can depend only on the modulus of x, and the time difference t, again because it is free particle, e to the I p dot x, once again only spatial difference because of spatial translation invariance. Then we found that this object has a very specific structure. It has a theta of t, which is more of convention, and then it should have the form exponential minus I, some function of p, which for convenience and with the future ideas in mind, we wrote as omega of p. It can depend only on the modulus of p, t. This is where we stopped in the last lecture.
2 by x2, is it spatial?
This one. No, this is an event. Psi at pq x2 is given by this integral at psi at t1 x2. Okay, so from some parameters. I'll try to be consistent. Whenever I don't put anything, it should be a forward pattern. Okay, so of course I can move once in a while.
Paddy, this after 2 pi over d, it should come in dy.
Obviously. This is wrong. Good. Thanks for pointing. This is this. Okay. So here also there shouldn't be a 2 pi. So these are just spatial integration. So in my convention there is no 2 pi in those things, and there are only 2 pi's here. Okay. So this is where we stop. Now let us go a bit further. So the first thing I want to do is to actually evaluate this for a non-relativistic part. Okay. Now, so for that I have to do this sum. I will describe how to do that in a minute, but you will find that throughout this course I will never evaluate a single path integral honestly. Okay, so there are tricks by which it can be done, and in fact the entire path integral procedure was produced in such a way that these tricks can be sort of justified mathematically in some form. So how are we going to do this? We are going to sum over the action for a free particle. Now the free particle action is just A, which is integral over dt of half m x dot square. The main point is that it is quadratic in the path x of t. So if it is quadratic in the path x of t, then if I want to use this sum, I can separate that sum and I can write this path as a classical path plus a deviation from the classical path. Okay? So what I am going to do is that in order to do the sum over all x of t, I am going to write any arbitrary path x of t as the path xc of t, which is the path for which the action is extremized, plus a deviation from that path, which I will call some q of t. So by definition, q of t vanishes at the end. I am supposed to sum over all the paths which go from x1 t1 to x2 t2. So if I draw a picture, so what we are doing is you have x and you have t, and you are starting from here and ending here. So you are thinking of paths like this. Okay, these are two representative paths over which I have to sum. Suppose I choose one of these paths to be the classical path, which I denote by xc of t. Then the other path can be always represented at any given time by giving the deviation. That will be my q of t. So summing over all paths is equivalent to just summing over all q of t, because this is a constant shape, so to speak. So the path integral which I have written down here, the sum over paths, this x2, x1 becomes sum over all q of t of the same thing, exponential I, capital A, now written in terms of xc plus q. Okay? But the boundary conditions on q are simpler, because q vanishes at the endpoints while xc has some x1 and t1, which I want to get rid of. So if you plug that into it, it is trivial. Since it is just a quadratic, you will have one term which is a of xc, then you will have one term which is a of q, and then there is a cross term. The point is that the cross term will vanish. Why does the cross term vanish? Let us just look at the cross term. The cross term is going to be 2 times xc dot q, xc dot q dot. So you are going to have a term which is like xc dot vector dot q dot, right? So you write this as d by dt of xc dot q minus, so you have taken the dot of this, minus q dot xc double dot. Right? When you do this, there is a double dot term, that is subtracted. Now, for a free particle classical path, this is 0. X double dot is equal to 0. This term, when you plug it in and do the integral, it will go to the endpoints, and at the endpoints q is 0. So that also vanishes. So the cross term will not come. Now this is a very general feature of all quadratic actions. So you take any action which is quadratic in the path. In fact, the coefficients can even be time dependent. You can have all kinds of other terms. But as long as it is of second degree, when you expand it about the classical path, the term which is going to come in the cross term is linear in Q. Now what does the extremum principle tells you? Extremum principle tells you is that if you change a variable slightly to the first order in that slight change, nothing should happen. The variable should, the quantity you are evaluating should not change. So to the lowest order in Q, which is first order in Q, you cannot have a contribution. So the term which is linear in Q has to always vanish. Okay? So you will pick up the contribution from this and you will get a contribution which is quadratic in deviation but not the linear. So this I can now write as, there is a action for this which is independent of Q. So it is A FC. This is the action evaluated for the classical path. Then sum over all Q of e to the I, the action evaluated for Q. Okay? We are done. Because when you do this sum, you are going to sum over all the paths with the boundary condition that Q vanishes at endpoints. Okay? Now, I don't care what this quantity is. Whatever it is going to depend only on T2 and T2. That is the whole idea of doing this shit. It's going to depend only on T2 and T1. And because it is a free particle and everything is independent, in fact you don't even need free particle. Because the Lagrangian is independent of time, that quantity can depend only on the time difference. So you get a very strong result that x2, x1 for any quadratic action, okay, I should say time independent quadratic action can be expressed in the form some function of the time difference times exponential I times the action evaluated for the classical trajectory. This is what I have called energy. Just some function of the time. Okay. So what is the classical action for a free particle? Free particles move with uniform velocity. So if you integrate, it is half mv square times t. V square is just the difference in space by time, because it's constant velocity. So it is x square by t square multiplied by t. So it is x square by t. So for the free particle, this is free particle. It is n of t exponential I m by 2, now I look at h cross, x square by t. Remember that x square stands for x2 minus x1 factorial square and t stands for t2 minus t. So this is what it is. Of course we need to fix n of t. But that is again trivial because we know what its Fourier transform is. We had worked out here that the Fourier transform of this quantity, that is if I take x2, x1 and I do the Fourier transform on this side, I know what f is and f must have this form. Okay? So first of all, it's a good consistency check, one should do that. And then you should be able to read out what is n of t. Okay? So in order to do that, we need to do a Gaussian integral on this. So let me do this. This is the first time we are doing a Gaussian integral. Okay, so what I want to do is to do the inverse Fourier transform of that. So I want to evaluate the integral minus infinity to plus infinity on x. So it is dv of x exponential. I will call this whole thing as ax square. Okay? Of course, x square now is a d-dimensional vector square. Ax square. And I have to do an inverse Fourier transform, so I need an e to the minus I p dot x. Of course, it separates it out into each integral. So I will just do one of them and write down. You need this integral, and this is a good thing to remember, at least till the end of this course. Minus infinity to plus infinity dx And it is nice to operate in this form without worrying about convergences and things like that. Ax squared plus bx is 5 by minus a to the power half exponential minus b square upon 4. The way it comes about is, if b is not there, probably all of you know that it is square root of pi by minus c. That is like a gamma function integral. Now when b is there, what you are going to do is to look at this ax square plus bx and write it as a into x square, okay, x plus b by 2a, the whole square, which is going to give you x square. It is going to give you b by ax, which multiplied by a will give you bx. But you have added something extra, you want to subtract that out. That will give b square upon 4a square. This is same as that. So this a multiplying this will give you a e to the minus b square upon 4a, which will hang around. This, after shifting x to x plus b by 2a, you can integrate it out. That will give you root pi by a. Okay? So this is the answer, and we have to just substitute it correctly here. So here I will have pi divided by minus a. Now let us plug in for minus a. So it is minus Im by 2 h cross. So 2 goes on top, h cross becomes 1. Im by 2 h cross and t goes on top. Rise to d by 2. Because for every dimension I get a half, and there are d spatial dimensions, so I get d by 2. Then I get an exponential minus b square. So b square is square of this. So each dimension will take care of itself, except that I will get a minus sign, minus b square upon 4 times a. A is again this, so this is I 2m and h cross we have set to unity and a t on top. Okay, so there is a minus and minus which will cancel out, but when the I goes to the top, it will regenerate a minus. So I just keep one minus, and this is what I will have. Okay, assuming all the maths is correct, this is the result. And here also it is method to write it as 2 pi I t by m time d. Fine. First thing, we have done the Fourier transform, and a Fourier transform better have this form. Of course, we did the Fourier transform of this part. There is an n of t multiplying. So what we actually need to do is this into n of t. Okay. That will give you this into n of t. And we already know that this must have this form. This is fine, but here I should only have a theta of t. That means n of t should be the inverse of this. That fixes for you n of t. So n of t has to be this quantity, m over 2 pi I t to the power d by 2. Therefore, the full action is this one. Now h cross is 1, x square by okay. So I want you to take a moment and understand what we have done. We wanted to evaluate the sum over parts for the free particle. We said that you can separate it out into the classical path plus a deviation, and you only need to sum over the deviation. When we did that, we found that because it is quadratic, you can write it as an exponential of the classical action, that is action evaluated for the classical path, times a function which is purely a function of the time difference. Right? But we have no way of determining what this quantity is. In fact, this quantity will play an enormously important role in our field theory discussion. This is what contains all the quantum fluctuations. This is just the classical part. Okay? In the WKB limit, when you ignore all the quantum fluctuations, you can approximate the sum over paths by the classical action, and you would end up getting this. This contains valuable information about the quantum fluctuation. But in the case of a free particle, it's almost trivial. So you have this NFT and we want to determine NFT. Now, in standard path integral courses, what they will do at this stage is to use the transitivity condition. But I have already used the transitivity condition and shown that the transitivity requires the Fourier transform of this quantity to have a very specific form. So you go and take a Fourier transform of this, which we did, and we found this answer. And then we say that this has to be of this form, otherwise something will horribly go wrong. Therefore, your NFT must have this form. Okay. So thereby we fix the form of NFT, and the full propagator is this, except for a theta of t factor. Okay, so this theta of t, as I said, is understood most of the time, but if you want it explicitly, I have written it. Okay. So there are a few further things which I wanted to do at this stage with this. First, a very trivial comment. This object should make sense. It is p square by 2m, which is the energy of the particle. So the phase which we have written down here is essentially going to be the energy. Okay. There are basic reasons why it is true. We will see it in a moment when we do the whole thing in Hamiltonian. Second, and more important, there is a consistency check on all this, which will hold, of course, but it is good to keep that in mind. We said at some stage that psi at x2 is given by integral over dt of x1, x2, x1 psi at x1. At this stage, it is good to explicitly write this down. Let me put this as this, and here also let me write it as t2 comma x2. Okay? Now suppose I take the limit of t2 going to t1. If I take the limit of t2 going to t1, left hand side will become just t1 and x2. Right hand side, this is going to take the limit of t2 going to t1, and I better reproduce the same dependence at t1. This can happen only if t, the coincidence limit of, let us say, x2, coincidence limit, same t, x1, is a Dirac double function. You may think of it as a limit, or if you are not too concerned about trigger argument, as well write it like that. So when these t arguments are the same, it should go to that. I mean, most serious mathematicians would say the limit of this going to this should be equal to the Dirac double function, because you don't want to equate a function to a distribution. So you have this condition which should hold, but you have just evaluated that quantity. And we can ask whether it holds, and it does. It does because this is just a Gaussian, and we know that the normalized Gaussian, and in fact this is just the normalization factor for us. It is just 1 upon sigma root 2 pi per dimension. Okay? So in d-dimensional space, when you take t going to 0 limit, this thing will become a Dirac double. So fine, that consistency check is satisfied. There is one more very curious feature about this, which I want to spend some time on. This is not done in textbooks, and I don't know why, but well, mainly because it has some connection with optics and it is no longer fashionable to teach optics in BSc level. I don't know how many of you would have learned, but there is a very interesting connection between what you have got here as a propagator or a kernel to a problem which has absolutely nothing to do with quantum mechanics or quantum field theory. It has to do with a problem in what is known as paraxial optics. Now I'm going to bring it up because it turns out that it has remarkable connections with quantum field theory. What we are going to do next will tie in very nicely with it. So I'm going to spend some time on it.
Yeah, so before you do that, so
Yeah.
here, if you don't have a free particle,
Right.
you said the cross term is not there because x double dot is 0.
That's right.
So if it's some general quadratic thing, you need x double dot.
For a general quadratic thing which is time independent, we will only discuss time independent cases. That is, the coefficients are all, the Hamiltonian or the Lagrangian has no explicit time dependence. And if it is quadratic, you can go up to this stage.
So this term that the x double dot term that you got rid of.
That will go away.
Oh.
A corresponding term will go away. Because if you take a harmonic
Yeah, so that's
oscillator,
what. So
Yeah, it
maybe
will
x double
always-
dot will be something times x. That's the reason.
but it will always be proportional to the equation of motion. That's very easy to see, because if I make a first order change in Q, you cannot have, if this is a quadratic functional, not just quadratic, some arbitrary quadratic functional, and I plug in this, I can have only three terms. One is quadratic in Xc, the other is quadratic in Q, and the other is a cross term which is linear in Q. Term linear in Q should have a coefficient which is 0 when equations of motion are satisfied, because the term linear in Q represents when I change my path by this small increment, how much does the action change? Okay? And that action has to, the extreme condition on this Xc tells you that that term will vanish. Of course, one can write down the most general quadratic functional and verify it explicitly, but you don't have to do it. Yeah. Now, let us proceed further to this issue of the so-called paraxial optic.
Q doesn't have to be small. Right?
No. Q need not be small. That is the whole point.
So then in your action principle, like you require that Q be small, right?
No. In action principle, when you make a deviation, you can write down the deviation in the action principle as a Taylor series expansion in Q. There is a first order term, there is a second order term, third order term, etc. What extreme condition tells you is that the first order term will vanish. If Q is not small, you will have contribution from higher order.
Right.
But it always tells you that if you expand it above the extreme one, first order term will vanish. Let me give you a simple example in terms of functions. Suppose I have a function f of x against x, and let us say this is the maximum point. Okay, this is where the function is a maximum. I am going to expand this function in a Taylor series about this point. I am not going to say it is a infinitesimal Taylor series. I am going to retain all the terms. Then I can write down this function at this point as a Taylor series expansion from here without assuming this deviation is small. But even then the first order term here will vanish because the f prime will vanish. Right? That is what we are saying. If it is small, then the higher order terms do not contribute. But that is not relevant for us. That is why you cannot use it for non-quadratic action, because there will be cubic terms and all that sort of thing, and we don't know how to handle it. Okay. So let me try to describe to you what this paraxial optics is all about. Let us think of a pure space diagram. This is the z-axis, this is x-axis, and this is y-axis. Real three-dimensional space. So you have a screen here, let us say, with a slit at the center. What you do in optics? And I am going to hit it with light from this side. And the light is going and it is sort of captured in a screen here. Okay? So you will have diffraction patterns and all that sort of standard optics. What I am interested in is asking, what is going to be the intensity of light at some point here coming from a hole? Okay? So, with respect to the intensity at the center, I will normalize it with respect to the intensity in the center. So, you already amplitude at, let us say, Z, this is this coordinate is z, and this coordinate let us take to be z equals, okay, let me take this as z2 and let me take this as z1. Okay, so the amplitude at z2 at some point in the transverse direction. So x transverse is a vector interplane. It has just two components, x and y. It is given by essentially the factor which is exponential I times the path length by width, 2 pi I times path length by width. The path length to that point from this origin, this is the path length L, divided by the wavelength of it. Right? Because that is the way the phases add up. I mean, if you are doing interference or whatever, you know where constructive interference is and destructive interference by this thing. So let us write it down. So this is going to be exponential 2 pi by lambda, let me call it k. So this is like k times this length. This length is going to be the path length between the two, which is z2 minus z1 the whole square plus the x transverse, which is the transverse difference. So just to be a little bit more precise, this has to be multiplied by the amplitude at the point where we are starting. So let me write at z1 and the x transverse 1 here. Z1 x transverse.
Yeah, so
The transverse x transverse takes care of both x and y. So you take any point here, and that point is taken care of by this vector symbol here. So there is a y and an x direction in this. So these are two-dimensional vectors. Now this is not a real surprise, and this is not the one which is connected to the propagator. Point comes here. I have introduced the concept of paraxiality. What is paraxiality? Paraxiality tells you that, okay, I'm going to assume that most of the light is traveling along the z direction with very little spread on the x and y. This is what happens in most of the optics. When you have a screen with a hole and a screen here, you don't expect light to go like that. I mean, it can, but that is not what you are interested in. You are sort of interested in a beam-like propagation. So I'm going to say that I'm interested in this situation where the lateral spread is small compared to the z direction spread. That is, this length is large compared to this. Then let me do a Taylor series expansion on that. So what I will then get is that this will become integral d x1 transverse a z1 x1 transverse exponential ik. Let me pull this out. So I get a z2 minus z1. Then I have, that has been pulled out, and I approximate the square root. So I get 1 plus half x2 minus x1. That I will now call just x transverse square upon z2 minus z1, which let me call as z. So this is also z. Okay, expand this out. So you get integral d x1 perpendicular a at z1 x1 perpendicular exponential ik z times exponential ik by 2 x perpendicular square Now what is this exponential ik? Is it? This is just the constant phase for the ray which is going along this line. And as I said, I want to normalize everything with respect to this, so I can sort of absorb it into this. I don't care. So this whole thing is some quantity which you have normalized by this. Then you get something here which should strike a chord. This is exactly of the form which we derived, and it is sitting here. It is mod x square upon t, and here you have mod x square upon z. In fact, if you say that the light is propagating with a velocity c, the mean time between propagation from here to here is proportional to ct. I could have put even ct here. Okay? And what determines here should have dimensions of some kind of a length, inverse length, and that is given by the wavelength of the length. Okay? So what does this mean? I mean, why is it that I am bringing this up? I am bringing this up for a particular reason. You have all done optics at some level where people have said that if I have a light beam here hitting there, then it is going to go and hit there. And then if I know the intensity here, I can compute the intensity there. But that is impossible. It just cannot happen. Because light is an electromagnetic wave. Electromagnetic waves obey second order differential equations in time. If I tell you the intensity of the electric and magnetic fields at a given point, you will not be able to tell me the electric and magnetic field at another point, until I tell you how it is varying with time as well. You can determine the intensity here from intensity here only if there are some hidden assumptions. Okay? And those hidden assumptions go under various names in optics like Huygens construction, etc. You take a particular thing and you propagate it forward and all that. Here what we are assuming is that the light is propagating predominantly in positive z direction. I am not going to consider light which is propagating in this direction. I am not even considering things going this way, that way, but I am certainly not considering that light. I am only going to consider this. Things are going only forward in z direction. Translate that into our context. We are talking about particles which are going forward in time. Your z is like t. So if you consider only paths which are going forward in time, then all that is happening in this complicated sum over paths and etc. is something like an optics interference. And the amplitude at a different point is given by the amplitude at one point multiplied by a kernel, which has exactly the same form as what you have here. But now you can do a little bit of a peep ahead. This was an approximation from this. And this one is what we have got here. What could this be an approximation of? Okay? That is easy to guess. You just have to take this denominator, square it, and add to this. Okay? Now the denominator there is t2 minus t1. So you would have liked to add t2 minus t1 the whole square plus this. Except that relativity tells you that when you add squares of time and space, you have to put an extra minus. So what relativistic particle will eventually do is to do exactly this, where this length will be given not by this expression but with a minus sign. Okay? So the proper interval between 2 points is what you will take, and then if you do this sum, you should get the full propagation without this paraxiality put in. This is what you should be able to apply, and this is what we will do. But what I was trying to point out that since same mathematics has the same consequences, what is happening in optics is what is happening in field theory and in quantum mechanics. And when you do that, you are no longer going to assume that things are only going forward in time. That should be obvious even here. Suppose you take this. This quantity is manifestly invariant under Z2 and Z1 interchange. T2 and T1 if I change, if T2 is greater than T1 and I think of the propagation in the backward direction and I interchange that, this doesn't count. But when I come up to this point, if I change T2 to T1, it picks up a minus sign. That minus sign turns out to be crucial. Okay, because it changes the sign of the energy, for example, when you do the, it is like changing the sign of Young in the action. If you put this minus sign, that is like changing the sign of M, or p square by 2m will become minus p square by 2m. So positive energy modes will become negative energy modes when I do that. So where did I lose that? Well, I didn't quite lose that. When I took the square root, I could have taken the square root with either plus sign or minus sign. I took the square root with the positive sign, saying that I am only concerning myself with this kind of a propagation. In the same sort of way, if you start with this kind of an expression in fully relativistic theory, and then you do the approximation that I am only going to concentrate myself with forward propagation, you will end up getting the non-relativistic. Okay? Fine. We will see all this as we go along, but I just thought I will give you a preview that an expression like this need not look very strange. That in a much more familiar context like optics, you will get an expression which is very similar to this. Okay? Fine. Alright. Now let us see what further things which we can do with that kernel. So the first question you ask is that, alright, you have a prescription for this propagator and you calculated it for a quadratic action. Now suppose you have some other kind of an action which is not quadratic, let us say some t minus b, the standard t minus b. Does any of this make sense? I get something here. Does it match with what I would have intuitively expected it to be? Okay, that we need to understand. So you want to understand the same propagator in standard honest to God quantum mechanics, which I want to introduce how it goes, because that is the picture which we will be using in field theory. So all this is sort of a motivational thing leading up to the field theory. So how do you do that? This is plain quantum mechanics, but since you might have done quantum mechanics in different ways, I will again just rapidly go through some of the principles. I am not going to derive anything, I am just going to tell you where it comes from. In quantum mechanics, what is central to you is the notion of observables and Hermitian operators which are connected with these observables or correspondence with these observables and their eigenstates. So what is, suppose I think of an observable which let us say is A of t. This is an operator corresponding to an observable. And I am going to use Heisenberg picture in which the operators change with time by the state vectors q. However, if you take the operator at this time and I look at its eigenstates with some eigenvalue E, let us say. So this equation will hold. Of course, this will have this label t because this is the eigenstate of this operator at time t. At a later time, the operator is different, therefore the eigenstate will be different. Now, the operators satisfy in quantum mechanics the law I a dot or I d by dt of a is a commutator h, where h is the Hamiltonian element. Okay, this is the fundamental law. What I would like you to verify is that I am going to work with things where none of the operators or the Hamiltonian has explicit time dependence. In that case, this can be integrated, and the solution is that a at time t is e to the I x t, a at time 0 e to the minus I x t. So this you can verify by calculating this quantity and showing that it is equal to this. You should do that. Okay, so we know this. Now let us consider the following. Let us consider this equation itself with this quantity. So what that equation will become is that e to the I h t, a at t is equal to 0, e to the minus I h t acting on T A. If we think of this whole thing as a unit, this is equal to A times T A, because I have just substituted here for this A and this I just put it here. Now what I want to do is to take this thing off and put it on this side. So this is again a set. Okay, this object is exactly what is sitting here. And it tells you that A at 0 acting on that state gives me again A times this, which tells you that this can be identified with the state 0, A. Because by definition, A at 0 acting on this should give me A times that one. Okay? So you have the result that T, I want to make sure that the signs in this is correct. Okay, let us proceed with that. So, I'm not completely sure, but it will turn out to be okay at the end. So, T A is going to be, this is e to the IHT times 0 E. That is, I take this equation and I multiply this by this and you get this equation. Okay. Now, suppose I also have, this also tells you that TA as a graph will be 0 A e to the minus IH. Because when I am taking the inverse, I have to take the complex conjugate of that, that will flip the sign of this. Now let us consider the following quantity. Suppose I look at T prime, A prime, T E. Let us look at this also. Okay? So this is going to be T prime A prime will be equal to 0 A prime e to the minus IH T prime from this, and TA will be equal to, I have written it here, e to the IH T 0. So together this is going to give you A prime e to the minus IH T prime minus T E. So here I have introduced this notation. Whenever you are looking at the states at T is equal to 0, by convention you drop the T label. Okay, so if I don't put that and I put only the eigenvalue, then that means it is evaluated at T is equal to 0. Those of you who know Heisenberg picture and Schrodinger picture will know that the standard convention is to identify those two pictures at T is equal to 0. Okay, so this could be thought of as either Schrodinger picture variables or Heisenberg picture variable. That's where the convention comes. Now, what I have done is on past this blackboard is essentially all of quantum mechanics, and in fact, people will say that this is all there is to quantum mechanics. What quantum mechanics tells you is that give me a whole set of operators corresponding to the observables. Then I construct their eigenstate. How do I compute the amplitude between one eigenstate to another? I could actually done it with two operators, A and B, but I am just sticking with one operator here. What does this tell you? This tells you what is the amplitude that at a time t, if I am in a state where an observable A had an eigenvalue A, that is, if I had measured that observable, I would have got the value A. What is the probability amplitude that at a later time when I make the measurement, I will get the value A prime. In particular, now let us go to AFT, which is the position operator. Okay, as I said, this thing works for any operator, but let us stick to position operator. Everything goes through exactly like this, and for position operator, when you do this, you end up getting an expression for the same thing without all these fancy path integrals. This x2, x1 can now be thought of as x2 e to the minus IX T2 minus T1 x. In fact, the only reason we believe in path integrals is because behind the blackboard we know there is this formalism which will support it. Okay. So what is this law has no ifs and buts, no quadratic action, this, that, etc. If you have a quantum mechanical system with a Hamiltonian head, then the amplitude for a particle to go at t from a point x1 at time t1 to a point x2 at time t2 is given by this also. You just have to value. Okay. Now there are two things which we have to do. First, for the case which we have studied for free particle, I have to show that this reduces to what we found, which is fairly straightforward. I will do it in a minute. Second, you have to show that this is same as the path integral. Okay, for an arbitrary Hamiltonian. That I may not do because that is not part of this course. Geiger would have done it in his path integral course. But I will just indicate where it comes from and leave the rest as an assignment. Okay, because there are some implications for doing it for the relativistic part. Okay, so first part first. So we want to evaluate this for a free particle. So for free particle, you don't need T2 minus T1, I can just have a T here. And I am going from some x1 to x2. Okay, it depends on, so you can think of it as 0 to T. So how do I do that? I introduce a complete set of momentum eigenstates. Because the free particle Hamiltonian only depends on momentum. So you put a P here, and you put a P here. And you integrate over ddt over 2 pi to the power n. Okay? So this Px1 is what we did in the last lecture. If you know, the mnemonic for that is this rule. This is your wave function in real space that has to come from x, p, psi with sum over p, so to speak. And we know that this is the momentum space, and our convention tells you that this is e to the I p dot x. Okay? So this quantity px comes in the other direction, so it is e to the minus I p dot x. Let us make sure that that sign is correct. This is psi x, this is psi p and px. And this is the convention I am using, that is correct. So e to the minus I p dot x1 is what you will get here. Then you operate on this eigenstate with this. That will produce for you e to the minus I omega p t. This h is just p square by 2m. So that acting on a momentum state will just give you the eigenvalue, which is what we have been calling omega p. Then you have a px2. From px2 it is straightforward. That is e to the I p dot x2. Okay? From this. This will have the opposite sign. So what you get here is that it is integral over ddt upon 2 pi to the power d e to the minus I omega p t e to the I p dot x. I won't bother to do this, but this will give you exactly the same result we did that. Because this is just, I mean, we have seen this in hundreds of different ways already. The Fourier transform of this is being given by e to the minus I omega p t. Theta function I have just excluded. So that omega p is p square by 2, which is what we found. Okay? So this matches. There are no surprises. And interestingly, in this way, it is very easy to see that consistency change. See, I said that this x2, x1 is x2, x1 e to the minus st. Take going to 0 limit. Then this just vanishes. Right? And therefore, you must have x2, x1 going to a Dirac delta function. Because the set and bra at x2, x1 is a Dirac delta function. Therefore, the limit of this when t2 going to k1 is a Dirac delta function. So it immediately comes. In this approach, if I put t is equal to 0, it's an integral over e to the I p dot x of the integral. Again, peeping ahead, what will happen in relativity, for those of you who know a little bit of quantum field theory, the d3p integration in relativity is not Lorentz invariant. In order to make it Lorentz invariant, it is mandatory that you will put a 1 upon 2 omega p here. That screws everything up. The moment you put t is equal to 0, you have e to the I p dot x divided by omega p. That integral is not a direct delta function. That is why x, y, the bracket, that amplitude is not a direct delta function. I told you that things cannot be localized and something will go wrong, and that is what you go. Okay, that is just to look at. So this is what we have got when we use this method using the Hamiltonian formula. Now I wanted to spend a little bit of time, I'm not going to spend too much time on that, explaining to you how you connect this up with the path integral formulas. Most of it will be in a handout or a note, but let me indicate to you how it is done. How it is done is to again go back to this amplitude. If you wrote down there, x2, x1, which is x2 e to the minus I p hat, which depends on p and depends on x times x1. This is what we want to evaluate and show that it is in some sense given by a path integral expression. Incidentally, this was first done in complete conceptual detail, not by whom you think did it, namely Feynman, but by Dirac. There is a very beautiful paper by Dirac in which he sets up the whole state and Feynman just polished it up. So you take this and you want to compute this quantity. The way you do this is to divide the time interval t into bits. So you take this 0 to t and you cut them up and in between things with a bit epsilon, and there are n of them, so n epsilon is equal to t. In the end, you are going to let this epsilon going to 0 and n going to infinity. This is called time slice. So at any in-between point, you can introduce complete set of states. So in particular, what you will do is to introduce a set of states, basis states like the xk, the position eigenstates and momentum eigenstates at in-between points, and write this whole thing as from x1 to, in fact the endpoints probably I should think of it as x0 and x or whatever. So you go from this to x1, then x1 to x2, x2 to x3, x4. So essentially this problem will be translated into evaluating the quantity x k plus 1 e to the minus I epsilon times this head xk. Because this t can also be written as n epsilon. So you write it as e to the minus I epsilon head, e to the minus I epsilon h, etc., etc. at each of them. Okay? So this is what it will get translated into. How do you evaluate this? You use the fact that, okay, the non-trivial thing is that h has a p and an x. If you are given some arbitrary strained Hamiltonian, let us say p cube times sin x, okay, I mean one can give a function like this, then it is horrendously complicated because classically you can have a Hamiltonian which is p4 times sin x, but quantum mechanically you don't know whether it has to be written as p4 sin x or p cube sin x p square sin x, p cube, whatever. And since p and x do not commute, all of them are different. So this is known as a factor ordering problem. So there is no solution to the factor ordering problem. You can only give a prescription. They will all lead to different quantum theories. But we will stick with things, I mean, we have enough problems to worry about without bringing these things in. So we will stick with things where the Hamiltonians are like p square by 2f plus bfx. Even then you are not out of it because the exponential of a plus b cannot be written as exponential of a into exponential of b because there is extra correction terms when a and b do not commute and b and bfx do not commute. So how do you tackle that? You tackle that by using the fact that this is epsilon. There's a very formal dictionary you can set up and show that you don't have to worry about it. But essentially what it boils down is if you write e to the power a into e to the power b, it will be e to the power a plus b plus correction terms, and the correction terms will be of order epsilon square. Now there is a trivial way of seeing this. So that is the trick I will use. You first say epsilon is small. So I can write this as 1 minus I epsilon h. So I am only interested in evaluating from this the quantity which is x k plus 1 h x k because of the epsilon. Right? 1 minus this, 1 doesn't matter, so there is the epsilon which I want to evaluate. Now here, this is the sum of two things. So this matrix element also is the sum of two things. One which involves p and one which involves q. Now suppose you have a quantity which is like some function of p sandwiched between these two. Okay? That is easy because you just introduce the pk against state stand. So this will become integral dpk over again 2 pi to the power d x k plus 1, forget vector symbols etc. for a minute, f of p pk xk. I'm just trying to indicate you how the maths works out. This thing you know, f at pk. This thing you know. So this is just the factor which we evaluated here. So it will just give you together a factor which is like e to the I pk dot xk plus 1 minus xk. So you know how to evaluate these kinds of things. Now we will look at the next kind of thing which you want, which is like, let me write it here, which is pure functions of x. If I just want to do x at k plus 1, f of just the operator x, xk. That is also trivial because this acting on this is just going to give you a delta function. So this is going to give you f at xk times a Dirac delta function on this, which just for fun you write as in the momentum representation dt pk over 2 pi d e to the I pk, which is exactly the same factor which is there, xk plus 1 minus xk. And of course you can take this f of x inside. So you find a very nice result that if it is f of p or f of x, you just have this Fourier transform with that f thrown in. So if I have a function which is the sum of these two, it again gives you the sum. So as a result of which, when you are working on the Hamiltonian, you get the result.